Hello, my name is Lumar Sunil and welcome to a video series where I'm developing this taxi game where you can drive around and pick up customers and deliver them to their destination. The game was developed in the programming language Zig and uses Raylib as a game library to help with things like rendering and playing music and sound and so on. So for today's video we're gonna focus on the pedestrian AI, and there's two things that I want to tackle here. The first thing is the pedestrians are walking all over the road and I want to avoid that, so we want to limit them to walk on the squares. And the second thing is that I want the pedestrians to kind of jump out of the way if the player comes in at them with a car. The pedestrians right now are just moving around the map freely. They don't have any restrictions where they're going, so they can wander onto the road and don't care if a car comes or not. So the first thing that I want to do is make them move into these square blocks and not go on the road. Okay, so we want to solve the issue with pedestrians on the road. Now let's draw some things here. Alright, and we have a couple of points. Now, what we want to do is we want to clamp the X value and the Y value of the pedestrian to be inside of this square. And how we do that is we say, so this is going to be the maximum of this X, which is the minimum, and the pedestrian. If the pedestrian is over here, then the X coordinate will not change. If the pedestrian is over here, then the X coordinate will change to be like this. Alright, and then we have to do the same for the maximum X of the square. This time we'll take the minimum of the maximum X and the pedestrian X. And there we go. So now if the pedestrian X is greater than this over here, then it will be clamped over to this value. If it's inside now, it will not get changed. So now we have clamped the X value into inside of this square, and we need to do the same for the Y value. And so now we're clamping both values into this square, which will keep our pedestrians in the squares. Okay, so in order to implement this, we need to loop through all entities that has the rigid body and pedestrians. So basically all the pedestrians. We create the iterator and we loop through each entity, and we call the clamp function for each entity. Now the clamp function looks like this. First we get the body from the pedestrian. We check if the body is already in one of the squares. If it is, then we return. And we already have a function for this, which is called isOnRoad. And we simply invert it to get if you are in the block squares or not. We get the body center of the pedestrian. The next thing we're gonna do is find the block which is closest to the pedestrian. So first we have these variables which keeps track of the one block that has the minimum distance so far. Then we loop through all of the city blocks. We get the distance from the block to the pedestrian, and we check if the distance is less than the current min distance. If it is, we're gonna set the min distance to be this and min index to be I. And now when the loop is done, we have the target block set to city block squares with min index, which will be the block with the least distance to the pedestrian. And then we set the position of the pedestrian body, and we take the position of the body and we apply this clamp function. And this function basically does what it said before. It clamps the vector components, so x and y, separately, and it uses this as a min vector, which is the target block top left vector, and this is a max vector, which is the target block bottom right vector. Now let's test this. And you can see that no one is on the road and everyone is kind of clamped into these squares. Alright, so the next thing we're going to do with the pedestrians is that they're kind of in the way when you're coming in like this, and we want them to move out of the way when you're coming in to them. So they kind of, oh my god, there's a car coming, and they will like jump out of the way. So let's say we have a car, and the car is moving in this direction. So this is the velocity vector of the car. And we're gonna need some pedestrians. The car is moving in here. We want the pedestrians to avoid the car by moving in these directions. So depending on where the pedestrian is in relation to the car, they will move in different directions. So since this pedestrian is above this line here, which is basically just the velocity vector of the car, except it's extended infinitely. Since it's above that line, we want this guy to move up, and this guy will move down. How do we actually know that this guy is going to move up and this guy is going to move down? So the first thing that we want to do is we want to take the perpendicular to this velocity vector. So we basically rotate it by 90 degrees like this. So we end up with something like this. So this is now the perpendicular, and we can basically extend it like this. It doesn't really matter what magnitude this vector has, we just want this line here. So to get to the desired direction, we need to dot product against this perpendicular line. And what do we do the dot product with? Well, we need to take this vector, which goes from the center of the car up to this pedestrian. So this is basically taking this pedestrian's position subtracted with the car's position, and you will get this arrow pointing towards the pedestrian from the car. And what you do then is you do a dot product, which basically points at this line here. So you do a dot product of this vector against the perpendicular car velocity vector, and you get a straight line onto this, and you get the scalar value, which in this case is positive. So we're gonna denote that as plus. And we're gonna do the same thing for the other pedestrian as well. And we're gonna end up over here somewhere, and we can see that this is below this point, so it's gonna be negative. And so we're gonna get these scalars, and depending on if the scalar is positive or negative, we know the direction that we're gonna move. So if it's positive, it means that the pedestrian is above this point. So that means that we need to move upwards. If we are negative, so down here, we know that we need to move down. Okay, so that's how you calculate which direction we need to move in. Okay, so the next thing we're gonna look at is how do we know when these two are trying to avoid a car or not? Well, we're gonna need to have some sort of rectangle in front of the car, or some sort of area like this, and anything within this area that is a pedestrian needs to run away. So that's how I implemented this, and it follows the velocity vector of the car. So the car is pointing this way, then this area is going out like this. If it's pointing upwards, then the area changes to be something like this. And the width of this area is calculated using the width of the car and then we have times some sort of factor, and we also have times the magnitude of the velocity itself. So the width actually depends on the velocity of the car and the width of the car itself. So it's just to give some sort of width to this rectangle here. Alright, so that's basically how the system works. Now I'm gonna show you how I implemented it in code. Alright, so here we are in the pedestrian AI system file, and we'll take a look at the code that implements pedestrians avoiding the player car. So here we have a function which is called every frame, avoid player car. And the goal of this function is to make the pedestrians avoid the car, but how it does that is first we get the rectangle, which all the pedestrians that are inside of this rectangle, we want them to jump out of the way of the car. So we're getting the rectangle here. We can go and look at this. So there's basically, I made two different actually branches in this function. So we want to check because if the player car is moving really slow and almost at a standstill, it can easily get surrounded by pedestrians and then being unable to move. So what I wanted to have is a behavior where the pedestrians that surrounds the car, if the car is moving really slow, even pedestrians that are like behind the car and around the car, everybody should move away from the car so you get free clearing to move forward with the car. And so we have a check here that checks if the speed is slow enough, and then we just calculate the rectangle, which should be the player car rectangle, which is this AABB here, and we scale it up by some amount, so it will be scaled a little bit so that pedestrians that are around the car will get inside of this rectangle and move away. If the car is moving fast, though, we want the rectangle to be in front of the car where the car is going, which we calculate over here. And this one, we basically have the calculation here. So we have the player body rectangle, so the player rectangle that goes around the car, and we move it in the direction of the velocity of the player, which we scale that by the width of the car. And so it will basically, if the car is moving to the right, then it means that the rectangle will be just next to the car in the right direction. And then we also scale the rectangle by some amount. So the scaling also depends on the honking sound. So if you're pressing G, that means your car is honking, which I made it a feature so that when you honk, you actually want more pedestrians to kind of react and move out of the way. So we have, when you honk, this rectangle gets scaled by 3. So you get a larger area that the pedestrians will move away from. And then we have this expand function, which is kind of a thing that I made up here. It's sort of like a scale, but it locks one of the edges in place and scales only one side of the rectangle. So for instance, if you're moving to the right, you want the rectangle to be on the right side of the car, but you want the left edge of the rectangle to stick to the car's right edge. And so the right edge of the collision rectangle will be scaled outwards, while the left edge of the rectangle will stay in place. And that's the rectangle. So let's get back to this avoid player car here. So we get the rectangle, which all pedestrians that collide with it will move away from the car. So we have to find all the intersections of that rectangle, and then we defer a 3 on that array because we need to. And then we loop through all the intersections and we get the entity here, and we also get the pedestrian AI. But since we might get other stuff that it's not a pedestrian, we use try get here in the ECS system to try to get something, and then we get a nullable component. So we have to check, is it null? If it's null, then that means that this did not have the pedestrian AI component, so it's not a pedestrian, so we can continue. But if it is a pedestrian, we also want to check if it's already avoiding the car. If it's avoiding the car already, we don't want to do anything either. We can just let the pedestrian avoid the car. But if the pedestrian is not avoiding the car and is intersecting with this rectangle, then we actually have to go in here where we calculate the velocity vector that the pedestrian will need to have in order to avoid the car. And let's look at that. So this is basically what I drew up in the diagram, but in code form. So first we are grabbing some stuff from the player. So we got the player body, position, velocity. And then we calculate the relative position from the player car to the pedestrian. So we take the pedestrian position and we subtract with the player position. Then we have some checks here. This is basically the same check as we did before with the player speed. If the car is moving really slow, then we want to do something else here. So if we're moving really slow and the pedestrian is behind the car, which we check by taking the dot product of the relative position of the pedestrian against the player velocity. So if this is positive, that means that the pedestrian is in front of the car, basically. And if it's negative, that means the pedestrian is behind the car. So we're checking here if we are moving slow and the pedestrian is behind the car. Then we want the pedestrian to actually just move away from the car in this way. We don't need to calculate if we're gonna jump up or down. We just take the relative position that it already has against the car and move in the same direction. So it will basically just move away from the car. And otherwise, we want to calculate if the pedestrian needs to jump up or down relative to the player velocity. So here we take the perpendicular to the player velocity by taking the player velocity and rotating it by 90 degrees, which this is defined as pi over 2. And then we take the dot product of the relative position against the perpendicular. So in the diagram, that means that if this dot product is positive, then the pedestrian is sort of upwards from the car velocity. If it's negative, that means that the pedestrian is downwards from the car, from the player velocity. So there we basically have our direction right here, and then we just need to calculate some sort of vector from that. So what we do is we take the perpendicular and we scale it by the sign of the dot product. So we basically get the same the perpendicular dot product. Doesn't matter how far away it is from the center, it just takes the sign of this, which means that if it's positive, it's upwards from the car. Sign will make that into a 1. If it's negative, then sign will make it into a -1. So it basically takes all, it can be any positive number, it will be 1, any negative number will be -1. There is an edge case here, which is 0, which means that the pedestrian basically has to be exactly straightforward from the car, which is very unlikely. So there is a bug here where the pedestrian will just stay put even if the car comes at them, but it's very unlikely, so I'm not bothering with that. And yeah, then we basically got our direction here, and then we have this min length function. So what this one does is basically you supply a vector and a length, which is the minimum length, and it will produce a vector that has minimum length of that length. So if you have a vector of length 10, and since we put in 100 here, that will be like scaled up to a length of 100. If you put in a vector with length of 200, nothing will happen, or yeah, it will just return the same vector. So it will still have a length of 200. So that's just to make sure that the jump away from the car has sufficient velocity, basically. So there we have our jump velocity, so the pedestrian will jump in the correct direction. And let's go down here. So this is where we grab it from this function here. Then we set the state of the AI pedestrian, the pedestrian AI, to be avoiding. And we also set the velocity here. I don't think this is used, but we set it here anyway. And we also set the duration of the jump to be, I think, 0.2 seconds. Yeah. And the way we do that is we set this next state at, which takes the global or the absolute time, and we add jump duration to that. And then we also need the animation, because we want the animation to run so it looks like the pedestrian is running. And then we also have this set velocity of the pedestrian's physics body, basically, to be the jump vector. So it will actually jump in the physics system as well. And as you can see here, the pedestrians are avoiding the car now. If you're driving faster, it makes them avoid further away as well. And here we can see when we're honking, they will react further away as well. Alright, so that's gonna do it for this video. Thanks very much for watching. If you have any questions about anything regarding the game or anything Zig related, feel free to ask down in the comments. And yeah, I'm gonna continue with working on the game for a little bit more. I'm gonna add some cars that will drive around the city and that you have to sort of avoid when you're trying to deliver the customers as well. So that will give some life to the city as well. I'm gonna do some more sound effects and add some music to the game. Alright, so that's gonna be it for today. See you next time. Bye bye.